Hello, everyone. Welcome to our presentation, Interpreting Interpretations, Organizing Attribution Methods by Criteria, at Fair, Data Efficient, and Trusted Computer Vision Workshop of CVPR 2020. As the development of deep neural networks in multiple vision tasks, interpreting the model's decision become more and more significant for the model to gain trust from human users. There are many different tools that try to interpret the deep models. While in this paper, we mainly focus on attribution methods that find the most important features in the input to explain the model's decision. Attribution maps try to assign scores for each input feature to explain its importance. However, we observe that different attribution maps can produce disparity, which may actually cause confusion or even conflict interpretations to human users. For example, attribution maps have disagreement of whether the lady is relevant for the model to predict dog in the example we shown. Therefore, the goal of this paper is to evaluate different attribution methods with numerical analysis to answer which attribution method is better at what extent. Recall that attribution method is defined by finding the most important features in the input towards the prediction. However, we notice that the importance is an ambiguous concept and that is hard to evaluate. Therefore, we firstly decompose the concept of importance into two complementary subconcepts, necessity and sufficiency. Necessity and sufficiency are originally two logical properties, and we adapt them into the context of deep neural networks by saying a feature or a group of features are more necessary than others if without these features, the model will lose more confidence than others. And we say a feature or group of features are more sufficient if with these features independently, the model will gain more confidence than others. How do we actually quantify the necessity and sufficiency? The first intuitive way is to simply incorporate the attribution scores as rank orders. We call this as ordering criteria. In a view of necessity, ablating the features with highest scores should jeopardize the output confidence than ablating other features. Therefore, ablating the features with the descending rank orders should produce the steepest curve showing on the right top. Similar to necessity, on the sufficiency side, adding features with an ascending rank order should produce the steepest increasing curve of output confidence. We call this necessity ordering or sufficiency ordering. There are many similar or related metrics doing what we described above, and they actually either fall into necessity ordering or sufficiency ordering. However, there is more than rank orders that attribution scores offer, and the actual values are overlooked by ordering criteria. So how do we improve rank order criteria? We introduce another criteria of proportionality. The motivations are, first, we believe the magnitude of attribution map also capture information, not just rank orders. Secondly, we want to interpret attribution scores linearly, which is saying, giving object feature x1 and x2. If their attribution scores z1 equals to 2 times z2, then we believe x1 is expected to be twice important than x2 is. Which is saying, if we are given two arbitrary groups of features, red region and the green region on the top of the feature, and they have the same share of total attribution scores, then they are expected to be equally important, either in a necessary way or in a sufficient way. We therefore evaluate if for any red and green pairs, ablating them will cause the same drop of output confidence for necessity, or adding them will cause the same increase of output confidence for sufficiency. Moreover, we do not want to go to another extreme that will condition on every pair of regions, independent of ordering, which would lead to sensitivity and another metric. We only define right squares from top to the bottom, and define the green features from bottom to the top rank orders. In the paper, we use TPN, total proportionality for necessity, to capture the difference of necessity between each pair of red and green groups, and we use TPS, total proportionality for sufficiency, to capture the difference of sufficiency between all possible red and green groups. In the implementation, we ablate features from the top to the bottom, and from the bottom to the top rank orders, which forms an area between the curve, the ones shaded with light greens on the right. For necessity, notice that x-axis is not the share of pixels anymore, but the share of attribution scores, which ensures each pair corresponding to each pair of corresponding points at two curves have the same share of attribution scores. Therefore, the area between curves actually measures the quantity of disproportionality, a quantity a good attribution method should minimize. Same rules are applied to the sufficiency shaded in light purple. Therefore, smaller area between the curves better the necessity or the sufficiency. We summarize our methods. Firstly, we decompose the way to incorporate importance into necessity and sufficiency. And we also decompose the concept of good attribution map into ordering and proportionality, which finally offer us 4 evaluation metrics. We use these 4 metrics to evaluate 7 attribution methods over 9,600 images from ImageNet on pre-trained VGG16 model, and the results are shown on the right side. We conclude that if a user only considers rank order is all they want, deep lift is recommended to show more necessary features, while GradCam or layer-wise relevance propagation are the recommended methods to locate more sufficient features. However, if the user also cares about actual scores being proportional to the importance, we recommend smooth gradient, salience map, and integrate gradient for necessity, and guided back propagation, layer-wise relevance propagation, and deep lift for sufficiency. Finally, we end our presentation by answering the question in the very beginning. With our experiment, we impart additional interpretations to these 2 attribution maps. GradCam highlights an area of sufficient features. The model can make correct prediction without the lady. However, among the sufficient features, higher scores do not strictly mean that those features are a lot more sufficient than features with lower scores. Therefore, the years and the head are not necessary to be equally important. On the other hand, smooth gradient highlights necessary features, and its attribution scores are actually proportional to actual necessity. Point clouds around the ladies are less intensive compared to the dog from the observation. Therefore, the lady is less necessary compared to the dog in the prediction towards dog class. Our work can be a good way to combine different interpretations by showing the user what is a reasonable way to interpret a particular attribution map for different neural networks. Thanks for watching our presentation. If you have any question, please contact us via the email. Thank you.